Hello, ladies and gentlemen, and welcome to our YSI webinar entitled How pH and ORP Sensors Work, Principles and Practice in Water Quality Monitoring. Today's pH and ORP webinar is the fourth part of a six-part YSI series that we are running, in which we cover various parameters within water quality monitoring. We're holding the webinars every Tuesday and hope that you'll join us for the upcoming presentation on June 16th, which covers dissolved oxygen, and our final webinar on June 23rd, which covers conductivity. So registration information for these upcoming presentations will be included in the follow-up email after this webinar. So for those of you who missed our first three presentations in this series, have no fear. We have them recorded and they are available. You could simply go to our regional website. The link is there on the slide, www.xylemanalytics.asia. By visiting this site, you'll easily find the banner which takes you to our webinar library. There we have a number of recorded webinars, including the YSI series, as well as an assortment of webinars from other brands within our Xylem organization. There are also a list of upcoming webinars with registration links that might be of interest to you. So feel free to check that out. For those of you who are new to GoToWebinar, you'll notice that the interface panel is sitting on the right-hand side of your screen. The audio settings are at the top. The second panel or second tab is for questions. These questions are for the question and answer session that we'll be covering at the end of the webinar. Feel free at any time to type out your question into the question box there, and we will include those in the questions we cover at the end of the webinar. The panel at the bottom, which is entitled Chat, this is for any questions you might have of a technical nature concerning GoToWebinar. If you're experiencing any issues with GoToWebinar, simply type out the issue there, and our marketing team, who is supporting today's webinar, will definitely get in touch with you. All right, and let's move on to our VIP guest today, Ben Sutter. He's our main presenter. He has a Bachelor of Science in Chemistry from Wright State University. You'll probably notice the name there. Wright comes from Wright Brothers, who are, of course, based in Ohio, which is where our YSI office is. Ben is a technical applications and support specialist. He has quite a diverse role. He's also the demonstration coordinator for YSI. He has 5 years experience working as a specialist on lab and field analytical equipment, and specializes in photometers, pH, and ORP sensors, ISES, and other electrochemical parameters. All right, quick overview. What are we covering today in our webinar? pH, ORP, what and why? The pH sensor, some history, types of sensors, and the construction of those sensors. Part 3 will be calibration, care, and practical use of pH and ORP sensors. And our final part for the webinar will be real-world applications for pH and ORP. All right, so before we bring Ben on, I'd like to launch our first poll question, which you should see on your screen now. Our first poll question is, what is your highest priority when selecting a pH or pH-ORP sensor for environmental monitoring? For those of you who are new to GoToWebinar, this is a separate window. Feel free to move your mouse over this window and select the answer that's most appropriate to you. Just click on that answer and these answers will be tallied. We'll show these momentarily. So while we're waiting for our audience to reply, I'd like to take this opportunity to bring Ben onto the stage. Hello, Ben.
Hi, thank you. Nice to be here.
Thank you. What time is it there in the US?
Right now it's 7:06 a.m.
Ouch.
Nice,
Well, we
nice and
certainly,
early in the morning.
definitely, we certainly appreciate the time you've woken up to join us today.
Absolutely. I love talking about stuff like this, and that's exactly what we're going to do today. Looks like we have a decent percentage of people who have voted now on our poll question. It looks like far and away accuracy of the measurement is going to be the most important thing. So that's good. We're actually going to go over a lot of things that'll help you increase your accuracy today. How long it lasts in my application was a runner-up on that one, and that's another thing we will discuss. We will discuss items related to longevity and accuracy of your pH probe here today. So let's go ahead and get started. First of all, we have some reasons to monitor pH and ORP. Basically, there's some major contributors to pH and ORP change. Soil and bedrock composition is something that you can change. Some dissolve more than others. Organic growth or biological activity, plants and animals present in the ecosystem. It'll help you monitor dumping and discharge, such as acid mine drainage or reclaimed wastewater. It'll also help you track acid rain from runoff or gases dissolved in the atmosphere. So those are some reasons why we should monitor pH and ORP. Now, why is pH so important in the first place? Well, here we have some labels on a pH chart to show you some approximate pH values for some common chemicals. Many of these are probably familiar to you, but it does illustrate the wide variety of substances where pH is a large part of the identity of that substance. For instance, we expect acids to be tart or corrosive. Now, pH acts as a hard limit for specific forms of life to exist within an ecosystem. We can see here that for a majority of fish, there's a limit to what pH the water can be before they cannot survive in it anymore. Human blood pH must be between 7.25 and 7.35, very narrow range, or blood hemes will fail to function. pH is vital to allow those proteins the ability to fold into a useful form. So if the pH is wrong, the blood won't work anymore. And sudden changes in pH or ORP may have to be correlated with events such as the day-night cycle or the rain events. How that data is interpreted is just as important as the values from that same data. So that's why pH is important. Now I'm mentioning ORP a lot. Let's talk about why I'm discussing them both simultaneously. There's just a lot of similarities between the pH and ORP probes. They both are using the same reference. Both are using the same hardware, oftentimes the same probe even. They're integrated in the same probe. They have a similar sensing bulb element. And they're both ion selective electrodes. If you don't know what those are, we are covering all of that today, so you are in luck. Measure in the same basic way. pH is more absolute and ORP is more relative. That is, pH, you can usually get the same number practically every time. And ORP, it's more whether your number has gone up or down, hence a relative measurement. And in general, speaking chemically, pH measures acid-base reactions and ORP measures redox, or that's short for reduction oxidation reactions. So pH is the measurement of hydrogen ions in water. It's sometimes called potential hydrogen. Aqueous solutions all contain some measure of hydrogen ions since H2O is constantly dissociating with itself. Here is water's chemical formula. It's our favorite chemical. Here's a model of what it looks like. Now, when water dissociates, what we end up with are two ions, the acidic hydrogen ion, sometimes called the hydronium ion, and the basic hydroxide ion, which is OH minus. The more hydrogen ions we have in a solution, the lower the pH value. And likewise, the more of the OH ions, of the hydroxide ions, the more basic we will be. let's talk about pH units. Units of pH are simply called pH units. They don't have a fancy name beyond what they're already called. Pure water has a pH of 7. Anything under is an acid. Anything over is a base. This chart shows us that scale. Once again, the more hydrogen ions we have in solution, the more acidic our solution will be. Let's define pH further. pH is equal to the negative log base 10 of the hydrogen ion activity. That logarithmic value in this definition gives us some important information, the most important being that for every 10-fold difference in hydrogen ion concentration, we increment a single pH point. We often call that 10-fold difference a decade. Here's an illustration that shows one of the major components or concepts of the pH scale, that for each pH unit we increment, we're also incrementing a 10-fold difference in our hydrogen ion concentration. You can see the advantage of the pH scale as it allows us to show huge differences in that concentration with a relatively small scale of pH, 0 to 14. In this chart, you can see that the H+ activity is mentioned up here. For the purposes of this webinar, we're going to consider activity to be the same as concentration. All right, let's talk about the important equation that allows pH and ORP probes to work, the Nernst equation. This equation is the basis for all ion selective electrodes, or ISEs, so it's worthwhile to look at the parts that we need for this equation. I've highlighted those in red, the parts that are actually going to change, so you don't have to look at this entire kind of huge, messy at first equation. Now, what the Nernst equation does is it establishes the relationship between the measured voltage and the ionic activity of the solution. Take a note of how it looks like the slope-intercept equation for a line. The beauty of this equation is that it allows us to express our measured concentration as a line. So y equals mx plus b is our slope-intercept equation for a line. In this case, E is going to be our voltage, T is going to be our temperature in Kelvin, A sub H plus is going to be our hydrogen concentration. So this image right here is directly from the pH handbook, all of our values here. Explains each of the constants and the other terms in the Nernst equations. The ones that we're interested in, that we're actually changing while we measure pH, are in red here. Everything else is constant. If you ever want to dig deeper into that, you can check that out. I put some links to the pH handbook at the end of this presentation. If you want to dig deeper into that, which can kind of be fun, then you can do that then. So let's look at the three values in the equation that we are interested in: voltage, temperature, and hydrogen ion concentration. The voltage, the E, that's the millivolt value that we'll see when we immerse the probe into solution. And it's defined as the measured voltage between the hydrogen probe and the reference probe. T, the temperature. That's why you always need to consider the temperature essential for a good pH reading, because the measured concentration is dependent upon the temperature. Then there's hydrogen ion concentration. If you can measure E and the voltage and T, the temperature, then we can solve for concentration. Here I've put the slope-intercept under the Nernst equation, so you can have an idea on how it will look when it is graphed. We'll talk more on that subject when we get to the calibration. We are going to see more of the Nernst equation. It is the key to all of this. So let's compare what we just learned to ORP. While pH measures acid-base reactions, ORP measures oxidation-reduction reactions. I may interchangeably say redox with oxidation reduction, but that is the same thing. As more electrons become available, the ORP becomes more negative. To be clear, there are no free electrons in solution, so we're really just talking about the chemical species that will either accept or donate electrons. What you see here is a version of a redox tower that shows several chemical species and their effect on the ORP readings. At the bottom, you see I wrote LEOGR. That's a mnemonic device. This is a device you can use to remember where the electrons are moving. It stands for loss of electrons, is oxidation, and gain of electrons is reduction. It's our little line there. Helpful reminder, the reminder line. Now we have ORP measurement. So the redox potential can be considered a measure of the ease with which a substance either absorbs or releases electrons. The expression electron pressure can sometimes be used. It's kind of abstract because free electrons don't exist in aqueous solutions, like we said, but the electrons come from the species being measured. ORP is also bound by the Nernst equation, except we replace the concentration of hydrogen ions with the concentration of all reducing or oxidizing species present in that solution. You can see here the diagram, the difference of signal you would get with a strong oxidizer, that's a permanganate ion, with a very weak oxidizer, which is the iodine diatom. All right, now we're going to move on to our next section. We're going to move on to the history, theory, and construction of pH probes. But first we have another question for you, poll question. Which of the following best describes your experience with environmental monitoring of pH? I'll give you about a minute to get those answers in, then we'll discuss the answers and see what else we can figure out. Lots of ways to monitor pH out in the field or in a lab. Quite a few different techniques for doing so, and they all have their own advantages and disadvantages. Looks like we have quite a few votes in. I think we may have enough information now. Looks like the number one answer, 40%, a pH sensor designed for the field, such as the EXO or Proteus S, one of our handheld systems. Second one is a combination sensor designed for field use. Those could be considered to be one and the same. That makes sense. You can also collect samples and measure pH in the lab. That's another valid way of doing it. We're going to go through a few different things here today on how pH is measured and how we can best do that and how that works. Almost everybody has measured pH in a science class using things as basic as litmus paper or as complex as a laboratory combination pH probe. Maybe you've had a chemistry course where you learned titration using color indicators. These are all good ways to measure pH, but they all kind of rely on you either looking at a color or a color change, and they're not super duper precise. Today, I want you to be able to understand YSI's unique field pH and pH ORP probes. They have a specialized design, enabling them to function in the open environment. The tools on the prior slide would not be able to accomplish this. First, let's talk about some of the fundamental principles of how pH is measured with probes or sensors. First is the pH sensor. A pH sensor will measure a voltage between 2 points when you get right down to it. There's two major portions of a pH probe. There's the glass electrode and there's the reference electrode. You should be able to see both of those there. There's a super basic version of what that looks like, but it's a good diagram for what we're trying to learn here. The glass electrode is where we will measure a potential. That's the part in contact with the measuring environment. That's the portion that you've immersed in your water, whatever you're testing. The reference electrode contains a reservoir of liquid with a known potential that is designed to remain unchanged. This is the electrode that is referenced when we look for a change in potential. Historically, these used to be completely separate probes, but now we combine those two into a single form factor, and we end up with a combination probe, which is what practically all pH probes are today. Many probes will also measure the temperature as well, with a thermistor built into the electrode. Otherwise, a separate temperature measurement is required. You do have to have that temperature. So I said a whole bunch of stuff about that, but let's get into what that means. Here's a simple diagram of the various potentials that are present in a typical pH probe. you can see that the glass electrode is separate on the right and the reference electrode is on the left. Again, typically these are combined into one these days. Voltage is a potential difference between 2 points. In the design of any pH probe, the goal is to have all of the potentials balance out with one another. That is, these potentials are accounted for in the construction of the probe so that at pH 7, our big U here, the big one up in the corner, big U should be equal to 0 millivolts, where big U is the total potential of the entire system. So we know that this system is designed to keep the potential the same so that we can measure the one potential that is actually changing, U4. In this diagram, U4 is the potential of the liquid that's in contact with the outside of the bulb. The solution will generate a millivolt response that the system measures. Since all the other potentials cancel out, we end up with a number to plug into our Nernst equation. Let me go back to here real quickly. You see we have all these potentials. Our goal is to get them all to cancel out, like we said. So if we're only changing this U4, then that U4 is going to be the only potential we really care about. So we can plug that into our Nernst equation. So as a reminder, the Nernst equation establishes the relationship between the measured voltage and the ionic activity of the solution. Here is our actual, right now we consider that U4 to be equal to E in our Nernst equation. We're just going to replace that here on the lower version of that. That is how, by establishing this potential and also by establishing the accurate temperature of the solution, we can determine the concentration of hydrogen ions and therefore pH, just by finding out how that one potential is changing. So pH and ORP probes are ISEs, ion selective electrodes. As a quick reminder, they're both ISEs, and this diagram of potentials and the Nernst equation is used with practically all of them. Oops, sorry. ISEs are designed to measure a single type of ion. The pH probe is just an ISE for the hydrogen ion. The ORP probe is an ISE for electrons, so to speak. So you may be wondering, how does the instrument know the difference between which ion is being measured? It comes down to the bulbs on the sensing portion of the electrode. And here is a schematic of the pH bulb. The bulb of the pH is where the hydrogen detecting ions are. It's the most delicate and arguably the most vital portion of the pH probe. It contains a silver chloride wire. That's the AgCl wire. You may be able to see that right in the middle there. Oops, pardon me. That silver chloride wire connects from the glass electrode to the reference electrode. The sides are composed of glass, although sometimes you'll not see this since it can be covered with epoxy or other material. It's filled with electrolyte solution that is selected to balance the potentials that were mentioned a few slides earlier. The most important part here, though, is still the bulb itself. It's very, very delicate, very, very thin, about 0.2 to 0.5 millimeters in thickness. Both the inside and outside are coated with an extremely thin layer of silica oxide gel. That gel is seeded with a substance that selectively looks for hydrogen ions, and this portion of the bulb is what creates that U4 potential that we were looking at previously. ORP bulbs are very similar to pH bulbs. All the internal components are essentially the same. If you have a combo pH ORP probe, very common, then this is the smaller bulb. Unlike pH, the silver chloride wire makes direct contact with the bulb, allowing electrons to flow into and out of the bulb to generate a potential. So that one's basically, you can think of it almost as shorting out one of the other potentials to get direct access to the electrons for an ORP bulb. Otherwise, all those internals are almost exactly the same. Let's talk reference junctions. At top here, you can see a few different reference junctions we have there. The junction is there to allow the filling solution of the probe to leak into the sample. That means that the junction must be immersed in the solution for the probe to work. If there were no junction, or if that junction were to be blocked, Then a vacuum would be created inside the electrode until the filling solution lacked the ability to flow. This lack of flow would cause drifting or unstable readings. It's the voltage version of holding your finger over a straw and trying to drink from it at the same time. So, do your best to keep that junction free. Different applications require different reference junctions, some of which are shown here. The differences lie in construction, materials, flow rate, and its location on the probe. We can see on this diagram that the U5 potential is the potential maintained by constant reference solution outflow. That is, as the solution leaves through the reference junction out into the water, it keeps all those other potentials equaling zero, so to speak, as we looked at the Nernst equation earlier. So that's absolutely vital to the function of the pH probe, having an outflow junction. All right, let's take a look at the Pellon junction. That's a special kind of junction. It's used with our environmental pH ORP probes. This junction resembles the wick of an oil lamp, and it works somewhat similarly. It allows the probe to be completely immersed in solution. The fill solution will leak out slowly from the cloth-like wick that connects the reference solution to the solution being measured. In the case of most of the compact handheld and Sonde-based pH probes, the reference solution is a 3.5 molar KCl gel. You can contrast that to lab electrodes that often use a liquid fill solution. Using a gel for long-term monitoring makes more sense because it does allow the probe to be watertight and very, very slowly release its fill solution. That will increase how long it can be out in the field. And both pH and ORP use the exact same reference reservoir if they're combination. You can see there the little circle here. It looks like a little wick sticking out. If you ever look at the bottom of one of your pH probes and you see a little piece of cloth, that's actually the junction. Here is what one of our XO-pH ORP sensors looks like. The black portion is the consumable replaceable module that contains the reference and the electrodes. The titanium housing connects the electrode to the instrument and contains the circuit board, which contains the calibration data. If anyone here is a pro DSS user, the design is essentially the same. You can see here the exposed portions of the bulbs for pH and ORP, and also down there is the Pellon junction that allows reference outflow. So little bulb is ORP, big bulb is pH, and here we have our little junction. And this is what they all look like. They don't, not every pH probe obviously has a titanium housing, but this one certainly does. Not all of them have circuit boards in there, but this one does. But you can see this is just what ours look like. All right, let's move on to our next section. The pH sensor, calibration, care, and practical use. We do have another poll question we'd like to ask you. When calibrating your pH sensor, how many calibration points do you typically use? Let's go ahead and see if we can get a scientific consensus on this one, and then we'll talk about how I like to calibrate, and we'll talk about the advantages and disadvantages of calibrating with various numbers of points. Calibration is something that very, very intimately familiar with. I've probably switched out and calibrated hundreds of pH probes, probably broken quite a few too. One good tip is a broken probe will not calibrate, but we will cover that, believe it or not. Looks like we have a good percentage of people who have voted here. And it looks like 40%, I'll just give the direct results this time. 40% of you said 2 points, 58% of you said 3-point calibration, and 2% 4 points or more. Okay, nobody put 1-point calibration. That's good. That's very good. We don't want to do 1-point calibrations here, with one exception, which we'll see coming up. All right, calibration basics. Why we calibrate. Every probe is different, so we must calibrate in order to establish the correct slope of the probe. The instrument will then save these established calibrations and use them to give us a pH value. The accuracy of the pH probe depends completely on the quality of the calibration. Let's talk about buffers. First of all, buffers are the standards that we use to calibrate. A buffer is a solution that can accept both acidic and basic ions without their own pH changing significantly. The most common buffer set is that of 4, 7, and 10, sometimes called USA or USA Blue Book. For a majority of applications, we want to use a 2 or 3 point calibration. As we will soon see, we need at least 2 points to establish a slope for a pH calibration. If you're going to do a 2-point calibration, always use pH 7 buffer as one of your points. Don't use a 1-point calibration for pH. You will not establish any slope with 1 point, and therefore doing a 1-point calibration does not actually help much. Avoid it if at all possible. There's other buffer sets too. You don't have to use 4, 7, and 10. You may see some other buffer sets in software for selection that have unusual values that are not whole numbers. A lot of them are historical throwbacks to when it was easier for a chemist to make up a specific recipe for a pH buffer than it was to get a nice even number as the pH value. For example, 6.86 buffer is made of 0.025 molar potassium dihydrogen phosphate and 0.025 molar disodium hydrogen phosphate. So those values would be pretty easy to measure out for a chemist. And it gives you a strange value for pH, 6.86. But if you see those old values, that's where those come from. Other buffer types, such as tris buffers for nucleotides, can be used, but only with probes specifically made to use them. Nernst equation's relationship to calibration. Let's quickly look at that so we can relate it to our calibrations. It is from this equation that we can derive the slope for our pH meters, which ends up being negative 59.17 millivolts at 25 degrees Celsius. This number, the negative 59.17 millivolts, represents the ideal span of voltage or potential for a single pH unit. The small text here is the math that gets us to that value as written in the pH Handbook, which we will provide a link to at the end of this presentation. All right. In pH 7 buffer solution, we do expect to have a measured voltage of 0, plus or minus 50 millivolts. This point is what we call the 0 point. In pH 4 buffer solution, 165 to 180 millivolts gets added to the 0 point measured in pH 7 buffer. In pH 10 buffer solution, 165 to 180 millivolts gets subtracted from that 0 point. Since we do know that 1 pH unit equals negative 59.17 millivolts at 25 degrees, we can easily see that 3 pH units at 25 degrees would give us negative 177.51 millivolts. So note the negative millivolts per unit. That negative slope does mean that explains why when we go to pH 4, which the number goes down, it has a positive millivolt value, and pH, which has a negative millivolt value, because of that negative slope right there. You can see right there on our little number line there, the span from 4 to 7 is that 177 millivolts, and the span from 5 to 6 is only 59. And that's going to be universal no matter which two numbers you go through. Any 1 pH change is the change of 1 pH unit is going to be negative 59.17 millivolts, ideally. So let's assume we're using buffers 4, 7, and 10. It's the same information here, but I've put it on a chart so we can visualize it. Note that a change of 3 pH units leads to a millivolt difference of that 177.51, which is within our acceptable range. We're about to go through a simulated calibration where we can populate the points one by one and see how an instrument would interpret those calibration points. So this is us walking through a calibration. Down in the left corner here, you will be able to see the points that are device, whatever our instrument we're using. That's going to be the calibration being drawn as we calibrate. So that will update as we go through these slides. A lot of you said you did a 3-point calibration, so now you get to see what the computer's actually seeing when we do that. Keep in mind that whenever you are immersing the pH probe into a calibration solution, you must assure that the reference junction and temperature probe are also immersed in that same solution. That holds true for each slide going forward. First, you want to begin the calibration procedure on your instrument. Tell it you're going to cal. Then you want to rinse your probe with the cleanest water you have available, DI, RO, distilled, or tap water in that order of preference. Gently shake off any droplets that cling to the probe. You then immerse the probe completely in fresh pH 7 solution. Allow your pH millivolts time to stabilize. We're looking for both the temperature and the pH millivolts to stabilize. Some instruments will automatically search for a stable signal and take the calibration point when it deems the signal to be nice and stable. If it's not automatically done by the instrument, you can then accept the first point. You just set your 0 point as shown on the graph, where pH 7 gave us a signal of 0 millivolts. It was a perfect pH probe in this case. For the second point, rinse the probe with a small amount of buffer that you're about to use. In this case, pH 4. Rinse it a couple times. You don't need very much, just a few teaspoons of that buffer ought to be enough to rinse it. Immerse the probe into fresh pH 4 buffer solution afterwards. Allow your pH millivolt time to stabilize. We're looking for temperature and pH millivolts to stabilize again. We expect this number to be 165 to 180 millivolts higher than the 0 point we just took. And you can see that on the chart as we start to see our slope shape up. If it's not automatically done by the instrument, you can then accept the second point. For the third point, rinse the probe with a small amount of buffer that you are about to use. Rinse it a couple times, then immerse the probe into your solution. Allow your pH millivolts time to stabilize just as before. We expect this number to be 165 to 180 millivolts lower than the 0 point we took at pH 7. If it's not automatically done by the instrument, accept the third point. This completes the calibration of the pH probe. Finally, our pH calibration chart is complete. We can see the entire slope. That right there is a perfect slope. So let's look at some calibration results so we can learn how to interpret those. Here we can see two calibration slopes for two different pH probes. Even though the slope of the green line has a 0 point that is negative 30 millivolts, the slope is still at the ideal negative 59 millivolts. The green arrow in the center of the graph here shows the 0 point at pH 7 can be anywhere, and that plus or minus 50 millivolt span, we'd still have a great calibration result, assuming that that slope is still good. There you go. That's my green arrow. You can see that if they had that same slope, that line could be anywhere in between those two arrows and it'd still be a perfectly good calibration. Bad results. So if you have a low slope, that's less than negative 55, absolute value of 55, I should say, and that's considered a poor response. So if we get to negative 55 millivolts, negative 54 millivolts, as that number gets closer to 0, it's just not as good anymore. See the two lines we have here. They look very similar, but one of them has a slope that's negative 46 millivolts, which is far off from the negative 59 to negative 55 that we're shooting for. As a result, the calibration represented with green diamond should be dealt with accordingly. We'll look into how to deal with that later in this presentation. But here we can see you would accept the good cal here, the one with blue squares, and you would not accept the calibration that had green diamonds in this case, even though they have the same 0 point. It's all in that slope. If your instrument says that you are out of range in terms of the millivolts, like we just saw, don't accept the calibration. Don't accept it. Check the millivolts of the calibration. If they're not within the range that's been discussed on any of the buffers calibrated with, we will have a bad cal. If you do accidentally accept it, you can restore the calibration to defaults on practically all YSI instrumentation. That will allow you to try the calibration again using a clean slate. So do keep that in mind. Let's briefly talk about ORP calibration. ORP is simple, it's 1 point. So I said a lot about 1 point calibrations, but in this case, they're very good. Use Zobel's solution to calibrate, a solution with a known ORP potential. Be sure to use the supplied documentation to match the temperature and reference type to the ORP value. Each calibrator will come with a document that gives the ORP value per temperature. We use the KCL reference in ours. When entering the value for your calibrator on the software for your instrument, be sure to input the one appropriate to the standard's current temperature. They should have a temperature chart. ORP is a relative measurement, so we do not need to establish a slope, just a 0 point. The change in ORP is arguably more important than the actual value, so the slope is less critical for ORP than it is for pH. ORP is a 1-point calibration, as mentioned. You want to set the ORP value on the calibration screen. It'll ask you what the ORP value of your calibrator solution is, so set it according to the current temperature that it's at and reference supplied with the solution. So you want to rinse your probe with the cleanest water you have available, DI, reverse osmosis, distilled, in that order of preference. Gently shake off any droplets that are clinging to that probe. Then you want to immerse your probe completely into the calibrator, which is Zobel's solution. It's kind of a iron-colored solution. Allow your ORP millivolts time to stabilize. We're looking for both the temperature and the ORP value to stabilize. Just as before, some instruments will automatically search for a stable signal and take the calibration point when it deems that signal to be stable enough. If not automatically taken, accept the calibration point and complete the 1-point ORP calibration. That's all it takes for an ORP. Troubleshooting your pH ORP sensors. So, assuming things don't go as planned, what can we do? First of all, let's look at clues that there is a problem. Slow stabilization during calibration, or it won't calibrate, can be an issue. If that happens, and that's such a frequent issue, we're actually going to switch slides here and get back to that. Buffers. Are your buffers expired? If they are, things could be growing in it. Gases could have dissolved into it, and they need to be replaced. Even though buffers do resist changes to their pH, they won't resist it forever. And over time, they are less and less able to resist that for the previously mentioned reasons. Don't reuse buffers. Once you have used them once, they're not a standard anymore. They have water, they have other things on them, they have residue from the probe. Don't reuse them once you've used them. Make sure that your buffers are the same as what is selected in the software. If you have NIST selected and you use USA buffers, there's going to be issues getting the good slope. Don't use TRIS buffers. They're not intended to be used with environmental pH probes. TRIS buffer literally reacts with the silver wire, creating a precipitate, clogging the reference junction, and you may think it may appear to be working for a short amount of time, but that will quickly stop. So don't use TRIS buffers, not with environmental probes anyway. You have to use a very specific TRIS probe in order to do that. Fouling, other things that can go wrong. Check to see if your bulb is dirty or if the reference junction is blocked. If it is, a 10-minute soak in dilute acid, such as acetic acid or 1 molar hydrochloric acid, can help clean the surface or clear that junction. Cracked bulb. Cracks may be invisible at most angles, but if you do have a crack in there, then that will basically short out that U4 potential that we discussed earlier. If your slope is a flat 0 millivolts on all standards, that's a good sign that you may have a cracked bulb. Lab only tip, reference hole is not left open. Some lab probes are refillable. If you do not open the fill hole, then you may have trouble getting a stable reading. It's basically like keeping your finger over that straw that we discussed earlier. Did the bulb dry out? This accelerates the aging process and creates micro cracks on the surface of the probe. Eventually that will also short it out. Was the probe stored immersed in DI water? This does the same thing as drying the probe out. DI water is really hungry for ions and it will ruin the outside surface of the bulb if you leave it in there to soak. And temperature. Does your thermistor work? And does the temperature seem reasonable? Is it immersed during calibration? And if the temp is on a different probe, is that probe also immersed? Basically, remember that we need to have that potential and we need to have the temperature in order to measure pH accurately. Without temperature, we don't have pH. All right, besides low stabilization during calibration, another issue that can occur is that it takes a long time to get stable measurements. pH and ORP, oops, sorry, troubleshooting. I'm sorry, that didn't do what I expected. If it takes a long time to get stable measurements, it's important to remember that pH and ORP probes are consumables. You should check to see if your probe has expired. As they age, small fissures on the surface of the silica layer on the bulb begin to form, which eventually will short out that U4 potential. As the probe gets older, the probe will usually tend to get smaller slopes. If it starts out at -59, it'll work its way down to -55 over the months until it has expired. For that reason, you don't want to purchase pH and ORP probes too far ahead of time. You want to check with the manufacturer to see what the recommended replacement times for your probes and modules are. You may want to have one as a backup. My recommendation, that's a good idea in case something goes wrong, but you don't want to buy, say, 5 years worth of pH probes all at once because they will degrade whether you are using them or not. So you want to buy them as close to the point where you think you're going to start using them as possible in general. Prevent fouling. We've had an entire series on this, or there's an entire webinar on this one, so I'm not really going to get too much into this, but do know that there are anti-fouling devices and products that we do have, copper components that fouling won't attach to. There's sea spray, there's shrink wraps. The important takeaway here is that if you're using an EXO and it has a wiper on it, you want to choose the right pH ORP module down here in the corner. That guard is good if you don't have a wiper, because then it'll help debris from getting onto the probes. However, if you have a wiper, you want that wiper to make contact with the bulbs and for long-term deployments. So in that case, don't use a guard on that one. And that's really all I have to say about that. For more information, please check out the anti-fouling webinar. Let's see. All right. Perform the calibration in a lab, or at least inside. Taking standards outside could make them change temperature. Oops, and it's harder to find stability on a moving target. Use fresh, unexpired solutions to perform the calibration. Don't reuse your calibration solution. Once you use a calibration standard once, it's compromised and it's no longer a standard. For pH, perform a 2 or 3 point calibration, not a 1 point. ORP only requires that 1 point. Assure that the junctions and bulbs are free of blockages and fouling, and use pH millivolts to troubleshoot. Take the guidelines here and see if your pH millivolts are in the correct ranges. Remember, those pH millivolt values define the calibrations. All right, to finish up, we're going to talk about some practical applications of pH and ORP probes, but first we're going to ask another poll question, get a little bit more information here. When your pH sensor is not going to be used for the next month or more, how do you store it? It's always great for tech support. We hear how they're always stored, but we'll have a quick discussion at the best way how to do that afterwards. I do thank you for all the responses. Thank you for participation. Much appreciated. It's really nice to have feedback live. That makes it so we can kind of tailor it to what you need to know. So let's see what we have here. 65% of you keep that in the storage solution that came with the sensor. That is the best answer. It's not the only right answer though. we highly prefer that you would keep it in that storage solution that comes with a sensor. Typically, it's KCl plus some preservative. I forget the exact chemical, some sort of phthalate. I think it's potassium phthalate, but we keep it in there. That's the best way to do that. pH 4 buffer is a good fallback. If you don't have the storage solution originally, pH 4 buffer will work just fine. The important part is generally that it has a lot of ions in there. pH probes love ions, so as long as you're not keeping it in DI water, you should be just fine. Storage of your pH and ORP sensor. See, we're jumping right into it. Keep the pH and ORP probe installed on your sonde or bulkhead for short-term storage. As long as your calibration cup has some water in it, the water vapor will prevent your probe from drying out. For more long-term storage, you may want to uninstall the probe from the instrument and keep the bulb soaked in a 3 molar KCl solution. That KCl has a high ionic content, very high. It's basically just very salty water. It's a good place for pH glass electrodes. You never want to let your pH probe dry out, and you never want to store your pH ORP probe submerged in DI water. Ever. Those are the things that will kill your probe faster than anything. That's why I put them in red. They definitely follow those guidelines if nothing else. DI water is very, very bad for pH probes. Sampling considerations for pH and ORP. pH of a body of water can be different depending on the location of a site. You want to sample in the same spot for good comparative data. You want to calibrate as close to your deployment time as possible to limit your effects of drift. Your pH calibration will drift especially over long periods of time. So you want to make sure that you calibrate that as close as possible to when you're actually getting that out to your water. Drift can be caused by exposure to the environment, and it's just the natural aging of the pH probe itself. So it is something that is to be expected, but it should generally happen pretty slowly, and it's generally something that you can mitigate by calibrating close to that deployment time. For ORP, ORP can give you a general idea as to how much oxidative potential there is in the water. This can be correlated with other factors to see how available oxygen is to break down or consume contaminants in the water. For many bodies of water, as you sample deeper down, the oxidation potential will drop. That is, the further down you go, the more your ORP will drop. So for comparative studies, you want to be sure to sample under the same conditions at the same depth in order to have the best, most comparable data. Stability will be greater in the standard, in the Zobel solution in this case, than it will be in the field. Zobel and other standards are made up of a single chemical of known ORP, but in water you have dozens of competing chemicals, typically in far lesser concentrations, which means you'll have some natural instability in the signal compared to having it in standard. You may have to report the ORP value as EH or E sub H. If you do, it's very, very easy to change that. EH value is just ORP plus 200 millivolts. It really is just as simple as that. You just add 200, and that's it. That's how you get EH. I'm not sure why it's reported that way sometimes, but now you know the conversion. pH and ORP in conjunction with other parameters. They are very useful parameters, pH and ORP, but they're several times more useful when you can correlate them to other parameters that you're also measuring. The more parameters you have to compare, the more correlations you can make. So this is a chart of about a month's worth of pH data from one of our exosondes. This particular sonde is at a site that YSI maintains in Florida for testing purposes. First, it may look like the pH is all over the place, but since we are logging points constantly, we are simply seeing the noise that's created by the day-night cycle. You can imagine that the mixture of ionic species in the bayou changes from day to night in a more or less predictable way. And if we were to smooth this data somehow, we could see the overall trend of the pH from week to week or month to month. Now, we're going to chart the dissolved oxygen along with the pH, we can see that it follows that day-night cycle very, very closely. As you keep on adding parameters, you can see how you could start to pick apart an event that was potentially incongruous with the overall data. In this example, we can see how the DO readings track well with the pH values, implying that the two parameters are changed by similar conditions. All right, now we're going to move on to another case we had. Here's a different situation, a little closer to home for those of us in Yellow Springs, Ohio. It shows how we can use our ORP to help corroborate data from other sources. In this case, several wells in the Great Miami River watershed were tested for arsenic. The initial tests were grab samples that were sent to labs for analysis. After arsenic was confirmed to be in a well, a secondary wave of testing was done. They would test the ORP of the wells by pumping the water up and out of the well and then measuring that water with an ORP probe. What they found was that in the water that was confirmed to contain arsenic, the ORP would trend towards being more negative. And you can see that chart kind of giving us that correlation right there. Here's another chart with a map. Here you can see two maps of the findings. The first map has the locations of tested wells and the concentration of arsenic that was found. Second map shows us measured ORP values in many of the same wells that had the highest concentrations of arsenic. To be clear, this ORP probe is not an arsenic sensor. It is not an arsenic sensor, but in this case, it can be shown that the correlation can help researchers come to some preliminary conclusions as to what is contained in that water. For a popular and extensive look into common problems with pH probes and their calibration, check out our ongoing water blog. Lots of great articles on various parameters, applications, and concepts. It's at ysi.com/blog. Also, please check out the pH Handbook. The YSI pH Handbook is a free publication of YSI. It goes into extreme detail on the measurement of pH. Many of the equations that were mentioned here today are explained, and you can learn a lot about the nitty-gritty details of pH measurements that we did not have time for in this presentation. Now I have more questions, and I believe now we have a chance to answer a poll question and perhaps do some audience participation questions if there are any. I'd be happy to go through that and see what I can do with that. But besides questions, that is the end of this webinar. So I do thank you for watching.
Thank you so much for your time.
Absolutely.
Yeah, thanks for your time. And we'll just give a few more seconds for the audience to reply to this poll question. Listen, I realize that we've hit our hour, but there are some terrific questions that have been queued up. And I'm sure the audience would love to hear your answers to them. So we do ask the audience to please remain with us. If you do have to leave due to time constraints, just a reminder that within about 30 to 60 minutes, you can expect to receive a follow-up email from GoToWebinar, which will include a link to this recording, as well as a certificate to prove that you actually did participate if you perhaps need that certificate. So I think we've given enough time to the poll question. I'll close that up, and perhaps we can move on to the final slide. Thanks, Ben. Just a reminder that next week, Tuesday, is the 5th part of our 6-part series on how sensors work. Next week, we'll be focusing on how dissolved oxygen sensors work. If you haven't registered, we highly recommend next week's webinar. It should be a fantastic presentation, and you can register at the URL that's displayed here on the slide, www.xylem-analytics.asia. It will also be included, this web address will be included in the follow-up email as well. All right, enough talking. Let's move into these questions. If you haven't asked a question and you are interested in asking one, simply type this out in the chat in the question chat box on your screen. All right, Ben, are you ready?
I am.
Okay,
What?
first question. Which pH sensor is better, gel-based or refillable, and why?
Okay. Well, I wouldn't use the word better in that case. It's more like more appropriate. Um, Gel has certain advantages in that it has a slow outflow. So if you want a probe that is compact and easy to maintain, generally gel is the way to go. For instance, all of our environmental probes, they must be gel filled because that's much more compact. It allows us to have a compact design that can go underwater and the whole thing can be immersed and work just fine. Refillable has many advantages too. I really like refillable ones because I work in labs often. You can put more solution in once it's outflowed to the point where it's gone too low. It arguably lasts slightly longer because you can keep on putting in more solution. So my short answer would be, for most environmental applications, gel filled is my preference. And for most lab applications, refillable is my preference. But both should work in a lab environment.
Great, thanks, Ben. So in your opinion, should the audience adopt a 2 or 3 point calibration over a 1 point?
The differences between a 2 and 3 are hotly debated amongst a lot of people. Basically, if you do a 3 point, you're doing a best fit, and it generally is a very good calibration. Because generally pH probes behave they behave the same way every time. They're pretty predictable. But if you do a 2 point calibration, you're getting some argue that you are getting a cleaner slope because then you're drawing a point between those two lines, or you're drawing a line between those 2 points rather, to get a very, very straight line. However, the difference between a 2 and 3 point calibration is very small compared to doing a 1 point calibration. So as long as you're doing a 2 or 3 point calibration, I would not scoff at either one of those. Those are both good choices.
Terrific, thank you. Is it possible to calibrate randomly, for example, 7, 4, 10, or 4, 7, and 10? What is the right sequence here?
I prefer starting with 7, and that's simply so you can see basically if your 4 or your 10 buffer was incorrect, you would not be able to instantly see that when you saw the millivolts. But if you start with 7 and you immerse it and you see that your millivolts are not within that positive negative 50 millivolts, then you immediately know that your pH probe is not working as it should be. So I would start with 7 simply because of that. 7's also the most neutral, and I like to start with neutral and work my way out. Personal preference, start with 7. The order you do any of the other ones doesn't matter.
Terrific, thank you. A member of our audience needs to check pH at a heavily polluted water. With a pH of 12, what would be the frequency of calibration that you would recommend?
Probably daily. Now, if you're doing a spot test, you're probably going to be calibrating pretty often anyhow. If it were a long-term monitoring situation, you'd want to calibrate it every time you get it out there. But with heavily polluted water like that, you can only benefit from calibrating more often. It may not matter to change the pH probe as much as you think. It may work just as it would in non-polluted water. The only thing I would be concerned about is clogging up that junction. So
Terrific.
practice anti-fouling, as if you are doing
That's
a
the
long-term.
key. Okay, great. Is there any special recommendation to prolong pH and ORP probes in seawater measurement?
Well, for a lot of probes, seawater will it'll make the situation more complex. However, for pH probes and ORP probes generally really like ions. So besides the salty crust that will appear when you have it in salt water for too long, which you can clean off, rinse off, there's really very few things to worry about having it in salt water. If anything, the probe may uh, to a tiny degree, it may even last longer from being in a high ionic strength environment for a long time, which it prefers.
On the topic of seawater, salt water, is there a calibration buffer for these applications?
Nope, the salinity really doesn't matter in terms of pH. What really matters is just the total hydrogen ion content. So for salt water or for fresh water, even for a lab application, I would be calibrating in exactly the same way.
Okay, terrific. We touched on this briefly before, but when calibrating, is there a specific buffer to start with, for example, pH 7, 4, then 10 sequence?
No, I think as long as you start with 7. Um, Personally, I start with 7 and then I grab whichever one is closest to me for the next one. Um, Again, 7 allows you to troubleshoot the most easily, and then we're starting from the neutral and working our way out. Um, it's just the best way to go.
Okay, the next question refers to um, a statement you made in your presentation using the term long term. When you
Okay.
use that expression long term, uh, can you give us an idea of what kind of time frame that would be?
Well, it depends on whether we're talking long-term storage or long-term monitoring.
Actually, it's not written, and I'm not sure which slide they were referring to. Perhaps you could relate to both.
Yeah. So when I think long-term monitoring, that's when you have a sonde that you're going to have out in the water for more than, let's say, a day. I'm not sure. I'm no I'm not out in the field measuring environmentally, but we do have sondes that you can keep out there. I would consider long term to be anything that you're going to leave out in the water and come back to later, and short term is going to be a spot sampling. Now, if they're talking about storage, which I'm imagining they are talking about, short term I would say is going to be anything less than a month, and long term is anything longer than a month. Everybody's going to have their own little definitions there. So if you ever really want to know, I would be specific and say, hey, is this okay if I do this for 2 weeks? In general, the when I said short-term versus long-term storage in this webinar, I generally mean less than a month, more than a month.
Okay, terrific. Thank you. On the topic of storage, can we store the pH probe in buffer for solution for short-term storage?
You can. That should work just fine. It has a ton of ions in it, and because it is acidic, it's less likely that bugs will grow in that buffer. Um, so that's a good second choice if you don't have the fill solution. Um, I have no qualms about putting that in pH 4 buffer. It's the second choice, but it's still a good choice.
Great. How long would you expect a pH probe to last for?
That depends completely on the probe. Um, a typical length of life for a lot of our probes is going to be about a year. But for some probes that have extremely high outflow that are designed to be used in harsh environments, it could be 6 months. That would be a very, very short amount of time for a probe. Some of them that have really good junctions and they have a ton of fill solutions, they could last maybe up to 2 years, but that would be a very that would be an outlier. I would say a year is pretty typical, and even if everything goes perfectly and your pH probe, you're taking care of it absolutely pristine, you're doing a perfect job. Even if you're doing that, eventually the silica layer on the outside and inside of that probe is the part that's eventually going to break down, no matter what you do, which is why it's important to calibrate. Basically, just once it fails a calibration, and you realize that slope is too low, then you're realizing that you probably are just dealing with an old pH probe, and that's when it's time to switch it out.
Great. The next question is quite interesting. Does the
Okay.
temperature of the buffer affect calibration, or does YSI auto-correct for this?
It is auto-corrected. So as long as you have your temperature probe in there, and a lot of times it's integrated directly into the pH probe, you just have to tell it that that's pH 7, and oftentimes it'll even automatically detect that because of the millivolt ranges that we have defined earlier. That's pretty universal. So if it sees that you're at 0 millivolts when you put it into a buffer, it will not only correct for temperature, it will also say, okay, well, this is probably 7 buffer that you just immersed me in. So yes, it will take care of the temperature. It'll take care of, in our newer instruments especially, it'll take care of the buffer selection for you as well.
Great, thanks. Okay, next question. Will continued use in very low pH waters wear the probe out quicker? For example, acid mine drainage monitoring.
It's a potential. If you have it in extremely low, like if you have it in DI water, then that's going to degrade the probe extremely quickly. If you're just in, say, tap water or something, that's probably not going to degrade it significantly faster than any other use. Even like acid runoff, that should be fine, unless it's attacking the probe itself with its strength, which is usually pretty rare. But unless it's so strong that it's going to actually damage the probe, it's very rare that that would be an issue. Again, the worst enemies for pH probes are deionized water, which will bleach ions from the surface of the probe and make it fail to work, or just leaving it out to dry, which will essentially do the same thing.
Okay, the next question concerns calibration. How frequently should a pH probe be calibrated?
The frequency matters completely on what you plan on doing with it. If you only use it once a week, just calibrate it, before you use it that week. I would say as the probe gets older, you probably want to calibrate it more often. If you're in a lab, you want to calibrate it every day. If you're going out into the field, you probably want to calibrate it every day. When it's brand new, you may be able to get away with every few days or maybe every week. If you really want to be sure, you can always put it back into calibration solutions and see what it reads. That is, if you're worried that your pH probe has drifted, just stick it in some pH 10 buffer or what have you, pH 4 buffer, and see how close it reads to that. If it's significantly off, just recalibrate.
Great. The next question is kind of a troubleshooting question. Let me know if you want to take this offline.
Okay.
I measure a number of streams with very low ionic waters, such as EC less than 40. I have trouble with getting stable readings. What do you recommend?
Well, that could be a couple things. The pH, if it's running water, that could be it right there. Since we're under running water, and if it's shallow enough, if it's a stream, it may just not be getting enough contact. You may have to take a grab sample. I'm sure if you took a grab sample of a stream and then measured that still water, then you would have a solid pH. It wouldn't be jumping all over the place. And if it is, it's probably down to the pH sensor being jumpy itself. A lot of times that happens in running water, especially if you have bubbles hitting it, bubbles going to be read as nothing. So if you have a lot of action in the water, so to speak, a lot of currents and eddies, then that could easily create an issue where you're not getting a consistent reading or you're not getting a consistent wash of water over there. So consider taking a grab sample, just put a cup in there and just measure the pH of whatever's in your cup. Try doing that to check to see if your pH probe is inherently stable anyway. The low ionic strength probably is not going to matter as long as you're measuring and then rinsing it off. That should not matter very much at all. So I think that's something they should consider a grab sample. They should consider maybe going to a thicker part of the stream or something like that. That could be quite a number of things. So we'll probably have to dig down deeper to find the true cause of that one.
Okay, great. Listen, we're running out of time. There's still quite a few questions here. Let's tackle one last question.
Okay.
Why is it that sensors like the NH4 CL being ISE sensors are not meant for use in seawater, whereas the pH sensor can be used in seawater?
That's a great question. So basically, we have something called a size to charge ratio of ions. And so a lot of times, if you have an ion that looks similar, like let's use the chloride ion, because we have a chloride ISE. A chloride ISE, a lot of things look like chloride. And when you're in salt water, a lot of things look like chloride. So it's basically overwhelmed with signal from too many sources. Now, hydrogen ions are so small, they basically have a unique charge to size ratio because they're small and they have a very specific charge. So nothing else really looks like pH. So pH you can use in that salt water and it's not going to be affected by the numerous other ions that are also in the water coming to the party and kind of throwing all our readings off. So it simply comes down to the hydrogen ISE, that is a pH probe. It's more selective because it is just because of the physics and the chemistry of it. It's just very, very much more selective. There's nothing that's going to compete with the hydrogen ions basically. And with all the other ISEs, we are seeing that competition. And because of that, we're never going to get a clear signal with all that competition in the water. I hope that came through clear. I'm not sure if it did.
I
I hope
hope
I
so
answered your
too.
question.
Sunish, that question came from Sunish. Hopefully he's happy with
Okay,
that. Great. Yeah, he just replied, yes, it did. So
fantastic.
fantastic. Yeah, good stuff. All right. To those who did ask questions, Wayne, Michelle, Johnson, there's quite a few of you out there who asked questions, and I do apologize. We don't have enough time to cover them all, but fear not. Either Ben himself or one of our regional sales specialists will reply to you offline later this week. So we will get back to you. Thank you everyone for attending this fantastic presentation, and a huge thank you to Ben. Thank you, Ben, for all your time.
Thank you for having me.
And ladies and gentlemen, we look forward to seeing you next week, Tuesday, for our 5th part of our series, How Dissolved Oxygen Sensors Work. Be safe out there and have a terrific day or night. Ben, have a great day yourself and hope to hear from you
Thank you
again
so much.
soon. Take care. Bye-bye.
Bye-bye, everybody.